So this is the second part of our lecture on solving exponential equations, and we're going to start working with the second method for solving. And the second method I feel is much more important than the first and much more useful. In method 2, we're going to isolate an exponential expression, and then we're going to take ln of both sides of the equation. We actually could take the log of both sides to any base, but I feel ln log base e is probably the most useful log for us to work with, so we're going to put a lot of emphasis on working with ln. This method always works, and what we're going to see though is that we're usually going to use a calculator to come up with a decimal answer, because we're going to have answers that are expressions involving logarithms, and it's kind of like we need the decimal to just figure out exactly what kind of number we've found or what the number is that we found. So we'll see that as we go through these examples. So let's go ahead and start a problem. Our first one is to solve 3 to the x power equals 10. It's actually a fairly simple equation to look at, and yet it really illustrates the power and the necessity for having logarithms here. Logarithms is what's going to allow us to unlock this situation. We have x in the exponent, so it's exponential equation. Also, we should just talk about how method 1 doesn't really work here, because we got base 3 on the left. I don't know any way to write 10 to base 3, right? Like 10 is 2 times 5. Those earlier examples in the preceding video, we had sides of an equation that were pretty straightforward to write in terms of one base. Here that's not the case at all. So I don't think method 1 applies at all. And it's also just kind of weird to think about what we're looking for, because we know 3 to the first power is 3, 3 to the second power is 9, 3 to the third power is 27, but 3 to what power is 10? What the heck does that even mean? Well, let's see what we find. When we go through the calculation, we'll go back and analyze our answer a little bit. So, all right, to apply method 2, we want to isolate an exponential expression. We actually already have the exponential expression isolated here, 3 to the x. So we're going to go right ahead and take ln of both sides of this equation. Ln of 3 to the x equals ln of 10. Okay. Now that gets us started. What's the use of this? Well, we can apply one of our laws of exponents that we, really the most useful law of exponents in this type of problem, is the law where we have log of a base to a power equals the power times the log of the base, log of n. And right here we can rewrite ln of 3 to the x as x times ln 3 equals ln 10. Now you can write parentheses around the 3 and the 10. When you have just a single number inside ln, the parentheses are really not required, but they're never forbidden either, if that helps you. And so the power of these logs and this law of logarithms is that we now have x outside of the exponent. This is just x times some number ln 3 equals ln 10. So to solve for x, I can just divide both sides by ln 3. So recopy, divide both sides by ln 3. The ln 3 is going to cancel, and we have x equals ln 10 over ln 3. And that's actually our answer. This is something we're going to call our exact answer, even though it's a little bit mysterious, because, like, what is it? And what is ln 10 over ln 3? Well, we're always going to, whenever we get ln's in an answer like this, I'm always going to want you to also approximate using calculator values. So just get my calculator out here, and 10 ln 10, I can calculate. It looks like that's, I'm going to round off to 4 decimal places, 2.3026 divided by ln3, so 3, hit my ln button, that looks like it's 1.0986, 1.0986. Now our answer x is what we get when we divide those, 2.3026 divided by 1.0986. And that's going to give me another decimal that I'm going to round off here. X is approximately equal to 2.0959. 0959. That's what I call the decimal form of the answer, or the decimal approximation. And so we're done, but I want to just say a couple more things about what we found here. One is, let's just try checking this decimal. Let's plug in to the original equation. Remember, the original equation was 3 to the x equals 10. To check, I would say, is 3 to the 2.0959, is that actually equal to 10, right? And I can, that decimal exponent has a weird interpretation, but there is a point with that x-coordinate on the graph of the exponential function 3 to the x. And I'm going to just plug in. I do have a button on my calculator for taking a number to a power. It's the y to the x button on this calculator. You should check and see on your scientific calculator how you raise a number to a power. You want to be able to do that. 3, I hit this y to the x button on mine, 2.0959. And what I get is, I'm not seeing 10, but I'm seeing 9.999999964, some extra stuff. That's not quite exactly 10, but that's very, very close. And there's a reason why I'm not getting 10 exactly. It's because the decimal 2.0959 was an approximation. And because I rounded off to get that number, when I plug back into the original equation, I'm just going to get a rounded off value here. If I had used my exact answer, ln of 10 over ln of 3, then I would get exactly 10 when I would take 3 to that power. There's no way to plug that into a calculator because the decimal for ln 10 over ln 3 is infinite, not repeating. And it's so as soon as we switch to calculator mode here, we're getting approximations, and even checking is going to be an approximation. But still, I think it's good to see, boy, still tells me I'm doing the right thing if I'm getting 9.999964. That is so incredibly close to 10. For all practical purposes, there's almost no distinction there. And so we got to write the exact answer. That's in one box. We got to write the decimal approximation. That kind of brings it to life a little bit in another. One last thing I want to say before we move on to is it's going to be tempting now sometimes to try to simplify these exact answers. Like, can I write ln of 10 over ln of 3 in another way? But ln of a over ln of b, when you have ln of one number over ln of another, that can't be written as a single logarithm. Just going to kind of put that in a bubble over here on the side. When we got that ln of 10 over ln of 3, don't confuse that with our laws of logarithms. One of our laws was ln of m over n, but that's really something different. When we write ln of a over b equals ln of a minus ln of b, which I'm trying to squeeze in here on the side, you know, that's really not the same as ln of a over ln of b. So again, these thoughts are separate from the steps of the problem, but I just wanted to get some comments here about, like, it's going to be tricky because sometimes we're going to think we see a law of logarithms that can be applied, and it can't. In fact, whenever we have one log ln over another, that cannot be simplified. We just have to, you know, that's not a law. That's on one of our yellow cards from an earlier section. Okay, so let's, I'd like to get through another problem on this video. So let's start looking at our second equation here. Solve 5 times 2 to the x equals 84. We want to solve for x. And this is similar to what we just did, but a little bit more complicated in that we want to isolate the exponential expression. So before I do this taking of ln of both sides like we did in the previous problem, what I want to do is isolate two to the x. I'm trying to write there. We want to isolate 2 to the x on one side. So I'm going to take that equation and actually divide both sides by 5 first. And so I get 2 to the x equals 84 fifths. And now I'm going to take ln of both sides. So that's what I mean by isolate the exponential expression, then take ln of both sides. This is always a preferred way to go. There are ways to take ln earlier, but then there are complications you'd have to deal with, so I don't want to go that way. We're going to isolate the exponential when we can. I can rewrite the left-hand side just like we did in the first example now, applying our third law of exponents. This exponent x times ln of 2 is equal to ln of 84 fifths. Now I'll keep the parentheses because I have something complicated in there. 84 fifths, if you prefer to write that as a decimal, that's fine. I'm just going to leave it as a fraction. And now to solve for x, I'm going to divide both sides of this equation by ln of 2. So then, other than having that fraction in there, this is similar to the problem we did previous. X is equal to ln of 84 fifths over ln of 2. There's my exact answer. And I want to also get a decimal. So let's see, 84 divided by 5. That was actually 16.8 inside that parentheses. Ln of that is about 2.8214 if I round off. I round off at 4 places. That's not an official rule. If you rounded off at more or fewer, I'd still take that answer. 2 ln. In the denominator, we have 0.6931. And if you're able, on many calculators, it's possible to carry out this whole calculation without writing down preliminary decimals. That's fine with me. If you can get right to this final decimal value, you don't need the intermediate steps. 2.8214 divided by 0.6931 equals, I'm getting 4.0707 when I round off. There's my decimal form of the answer. Answers may vary slightly. By answers, I mean decimal answers may vary slightly. Because different people may round off at different parts of a problem, and they're both correct. There's no rule about exactly where you do the rounding or when you do it in a problem. And so that can lead to slight variations. So I'm aware of that, and just you should be aware too when you check an answer. If you're very, very close to a decimal, you're probably just fine. We want the exact answer also with logarithms, because one thing is, if you want more accuracy from an answer, there's not really any way to take this decimal and get a more accurate answer. The advantage of the logarithm answer, the mathematical answer, is you can use this ln expression to get any desired degree of accuracy. Maybe you want 10 decimal places or more. You can always get that from the original answer. We couldn't get it from our rounded off decimal, even though we kind of like that 4.0707, because I would have no idea looking at that logarithm expression that we're talking about a number that's very close to 4. So I'm going to stop part 2. We're going to do some more examples, but that will be on another video.